Your team just had the best sprint in company history. 47 features shipped in 2 weeks. The AI tools were humming, Cursor autocompleting entire modules, Claude Code wiring up API integrations, the PRs flying through review because everything looked clean and coherent. Then, 3 days after release, your payment processing pipeline silently starts dropping transactions. Not crashing, dropping. No errors, no alerts, just money disappearing into a void. You dig in. The root cause, an AI-generated retry handler that was syntactically perfect, logically reasonable, and completely unaware that your message queue guarantees at least once delivery. The result was duplicate charges on roughly 2% of transactions, which at your scale was $18,000 in refunds and a trust crisis with your largest enterprise client. The code passed review because it looked like good code. It passed tests because no one had written a test for a distributed systems contract that lived only in your team's institutional memory. This is not a hypothetical. Variations of this scenario are happening right now across every team that adopted AI coding tools without reinforcing the engineering discipline underneath. And by the end of this lecture, you will know exactly what that discipline looks like. So let's name exactly what happened there, because it is not a bug story, it is a structural story. AI coding tools like Cursor, Claude Code, and Grok are genuinely extraordinary at one specific thing: converting intent expressed in natural language into syntactically valid, stylistic consistent, locally coherent code. That phrase, locally coherent, is the key. They optimize at the function level, the file level, sometimes the module level. But software systems are not collections of locally correct functions. They are networks of contracts, explicit and implicit, state, ordering, ownership, and failure behavior. And here is the core paradox. The faster an AI tool generates code, the more invisible the structural debt becomes. Because when you write code slowly by hand, you are forced to think through the system context. You feel the friction of wiring things together. That friction is information. It is telling you that this integration is more complex than it looks. AI tools remove that friction, which feels like productivity, but they also remove the signal. The teams most at risk are not the ones ignoring AI. They are the ones who adopted AI tools fastest, shipped the most features, and now have a codebase that is wide, fast, and structurally hollow. But here is what makes this fixable, and this is what we are going to build together. The developers who are actually winning with AI tools right now are not better prompters. They are better engineers, and the difference is specific and learnable. Let me be concrete about what you are going to walk away with from this lecture series, because vague promises about being a better engineer are not useful. Here is the specific capability you are building. By the end of this series, you will be able to take a real-world problem statement, for example, build a customer support automation system, and decompose it into a multi-agent architecture where each agent has a clearly defined contract, its inputs, its outputs, its failure modes, and its integration boundaries. You will not be doing this with prompting tricks. You will be doing it with problem decomposition, separation of concerns, contract first design, and failure mode analysis. SWU engineering principles that have been battle-tested for decades and have now become the primary competitive advantage in the AI coding era. Specifically, after this series you will be able to identify where AI-generated code is structurally safe versus structurally risky in a codebase, define agent boundaries using interface contracts rather than implementational intuition, write specifications that AI agents can reliably, instead of prompts that produce plausible-looking but fragile outputs, and review AI-generated multi-agent systems for the class of failures that look correct locally but break at the system level. These are not theoretical skills, they are the exact skills that separate the engineers getting promoted right now from the ones stuck in an endless loop of AI-generated technical debt. So the question is not whether AI tools are powerful. They are. The question is whether you have the engineering foundation to direct that power. And that is exactly what we are building here. Now I want to plant something in your mind before we go any further, because this is the claim that most engineers resist when they first hear it, and then cannot unsee once they accept it. The developers who are winning with AI tools right now are the ones who write the least code themselves, not because they are lazy, not because they have the best prompts, but because they have internalized something that most developers have not. That in the AI coding era, the scarce resource is no longer code production, it is structural judgment. Any developer with a Cursor license can generate 500 lines of code in 10 minutes. What almost no one can do reliably is look at those 500 lines and say, here is where this will fail at the system boundary. Here is the implicit contract it violates. Here is how to decompose this differently so the AI can execute it safely. That judgment, that architectural thinking, is what separates a developer who ships features from a developer who ships systems. And here is the part that should make you genuinely curious about what comes next. The SW engineering fundamentals that give you that judgment are not new. They have been in textbooks since the 1970s. But almost no one applied them rigorously in the manual coding era because the cost-benefit was marginal. In the AI coding era, the cost-benefit has flipped completely. And in the next chapter, we are going to go through exactly which fundamentals matter most, why they matter now more than ever, and how to apply them in a world where your coding partner generates 1,000 lines before lunch. Let's reset the definition. Most people, when they hear software engineering, picture someone writing code. That is exactly the trap. Software engineering is the discipline of transforming an ambiguous human need into a reliable, maintainable, and verifiable system. And coding is just one narrow slice of that pipeline. The full scope covers requirements elicitation, system decomposition, role separation, interface design, verification, integration, and operations. Remove any one of those and you don't have engineering, you have hacking. And here is the uncomfortable truth for 2025, AI tools have gotten extraordinarily good at the coding slice. But every other phase, still entirely on you. The question is whether you actually know what those phases are, because if you don't, you won't even notice when they go missing. And that is precisely where production systems break. Next, let's see whether switching from human developers to AI agents changes any of this. And now here is what changes when you swap human developers for AI agents, and what does not. On the left side, picture your classic human team. A product manager clarifies requirements, a tech lead decomposes the system, individual developers own modules, and a QA engineer verifies outputs before integration. On the right side, picture a multi-agent system. An orchestrator agent receives the task, sub-agents are assigned to modules, each produces output, and the system attempts to assemble a final result. Look carefully. The execution actors changed. The phases did not. Requirements still need clarifying. Decomposition still needs deciding. Interfaces still need defining. Verification still needs running. Integration still needs managing. The structural invariants of software engineering are completely untouched by the shift to AI agents. What this means in practice is that every failure pattern we saw in the previous chapter, the fast shipping, fast breaking cycle, traces back to skipping one of these phases. Not to the agents being incompetent. The phases were skipped because the human orchestrating the agents did not know to enforce them. That skill gap is what this lecture is about. Let's talk about where AI agents genuinely break down, not because they are poorly built, because of a structural limitation that no amount of model improvement fully resolves. AI agents execute within a defined context. They are exceptional at that, but they cannot define the context itself. Consider requirements ambiguity. A stakeholder says, build a reporting dashboard that is fast and easy to use. Every word in that sentence is a trap. Fast means what? Under 2 seconds? Under 200 milliseconds? For how many concurrent users? Easy to use for whom? A CFO who opens it twice a month, or a data analyst who runs 40 queries a day. An experienced engineer hears that sentence and immediately generates a list of clarifying questions. An AI agent hears that sentence and starts building. It will build something coherent, something that looks impressive in a demo, and something that will fail the first time a real user sits down with it. This is the problem framing gap. The agent operates inside the box. The engineer defines the box. And if the box is drawn wrong, everything inside it is wrong too, no matter how perfectly the agent executed. Here is what makes this even more dangerous in a multi-agent setup, which we will cover next. Now let's look at the second critical skill, interface design and contract definition. This is the engineering decision that determines whether a multi-agent system can ever integrate its outputs, or whether it generates an expensive pile of incompatible components. Here is the sequence that matters. Before any agent writes a single line of code, someone must define what each module produces, what format it produces it in, what assumptions it is allowed to make about its inputs, and what guarantees it must provide to its consumers. That is a contract. In traditional software engineering, this is called API design, interface specification, or in formal methods, pre- and post-conditions. When you have multiple developers working in parallel, the tech lead defines these contracts upfront precisely, so that when the modules come together, they fit. The same logic applies, identically, to multi-agent systems. If the orchestrator sends 2 agents to build separate modules without defining the interface between them, each agent will make its own assumptions. Module A will return a JSON object. Module B will expect a flat array. Integration fails. And debugging that failure is dramatically harder than preventing it, because the failure appears at the seam, not inside either module. Interface design is not a bureaucratic formality. It is the load-bearing wall of parallel development, human or AI. Next, we'll see that this principle is not new. It has been validated across 5 decades of software history. Here is what makes me confident that the skills we just described are not going away. History. Every major leap in software scale has been solved by the same underlying principle: divide and conquer. In the 1960s and early 70s, Dijkstra and the structured programming movement recognized that monolithic, unstructured code was unmanageable as systems grew. The solution was decomposition, break programs into subroutines with clear inputs and outputs. In the 1970s and 80s, modular design extended this idea to entire systems. Parnas introduced information hiding. Modules expose interfaces, hide implementation. Teams could work in parallel because the contracts between modules were stable. Fast forward to the 1990s and 2000s, object-oriented design, then service-oriented architecture, then microservices. Each one is divide and conquer applied at a larger scale, with stronger interface contracts between the divided parts. And now, multi-agent systems. Same principle, different execution layer. The remarkable thing about this history is that every time the execution layer changed, from assembly to high-level languages, from monoliths to services, the engineers who mastered the structural principle adapted fastest. The ones who only knew the syntax of the current layer got left behind. That pattern is repeating right now. Let me make the central argument of this chapter completely explicit, because this is the insight changes how you approach everything in the rest of this lecture. Multi-agent architecture is divide and conquer, automated. That is not a metaphor. When an orchestrator agent breaks a task into subtasks and assigns them to specialized subagents, it is performing system decomposition. When subagents communicate via structured messages or shared schemas, they are communicating through interface contracts. When results are aggregated and verified, that is integration and verification. Every step maps directly onto the software engineering phases we opened this chapter with. This means two things. First, if you understand software engineering deeply, requirements, decomposition, interface design, verification, integration, you already understand the structural logic of multi-agent systems. You are not starting from scratch. Second, if you skip software engineering and jump straight to prompt engineering and agent tooling, you will build systems that work in demos and collapse under real conditions because you are process you do not understand. The automation amplifies what you know. It also amplifies what you don't know. Mastering software engineering is not the old way of doing things. It is the prerequisite for doing the new things correctly. In the next chapter, we go inside a real multi-agent system to see exactly how this plays out at the architecture level. Let's open the hood on a real multi-agent coding pipeline and look at what's actually happening. At the top sits the orchestrator agent. Its job is not to write code. Its job is to read the problem, decompose it into discrete subtasks, and dispatch those tasks to specialized worker agents. Think of it as a tech lead who never touches a keyboard. Below the orchestrator you have worker agents, one handling API design, one writing business logic, one generating tests. Each worker has a narrowly scoped context. Then at the bottom sits the verifier agent. It receives all worker outputs, checks for contradictions, runs sanity checks, and either approves or sends tasks. Now here's what's striking. This is just classical SW engineering roles, architect, developer, QA, mapped onto AI agents. Grok's multi-agent implementation literally mirrors this pattern. The architecture isn't new. Only the execution layer is AI. And that distinction matters more than most people realize, because the next question is what actually happens when those workers run at the same time. Here's a claim that surprises most developers. Parallel agent execution does not automatically mean better results. It means faster results only when your tasks are structurally independent. The moment two agents depend on shared state. One agent writing a database schema, while another agent writes the query layer against that schema, you have a race condition in your reasoning pipeline, not just your runtime. This is the hidden dependency on problem structure that most multi-agent tutorials skip entirely. In software engineering terms, you need topological ordering of your task graph before you can safely parallelize. If task B reads output from task A, running them in parallel produces garbage. The agents aren't stupid. The decomposition was wrong. High-performing multi-agent systems like those benchmarked on SWE bench don't win because they run more agents. They win because someone, a human engineer, defined task boundaries correctly before the agents ever started. Parallelism is a reward for correct decomposition. It is not a substitute for it. And the question of how agents actually share information between those parallel lanes, that's where things get genuinely complicated. Now let's talk about the communication layer, the part that almost every blog post about multi-agent systems glosses over. Each agent has a context window. That context window is its working memory. When one agent needs to hand off results to another, that handoff happens through message passing, essentially structured text passed between agents. And this is where the same coupling problems you see in monolithic codebases show up in a completely new form. If Agent A sends a loosely formatted, ambiguous output to Agent B hallucinate its interpretation of what Agent A meant. There's no compiler to catch a type mismatch here. The interface contract between agents has to be defined explicitly. What fields are expected, what format, what constraints, before any agent runs. Think of it as an API contract between services. If you've ever worked on a microservices system where two teams made assumptions about each other's response schema, you know exactly how this fails. The stack here is task definition at the top, message schema in the middle, and execution context at the bottom. Skip the middle layer, and your agents are essentially shouting at each other in different dialects. And when that communication breaks down at scale, you get failure modes that no one on the team can reproduce. Let's put two worlds side by side and be concrete about the failure modes. On the left, a mulchant pipeline built without explicit role separation. No defined contracts, no clear task ownership. What happens? Two agents independently generate integration logic, slightly different implementations, both plausible. The integration agent receives both, can't reconcile them, and either picks one arbitrarily or merges them into a broken hybrid. No one planned for this collision, because no one thought through who owns what. On the right, a pipeline built with clear role contracts. One agent owns auth. Its output schema is predefined. The integration agent expects exactly that schema. Conflict is structurally impossible. Here's the uncomfortable truth. The failures on the left don't look like AI failures. They look like ordinary integration bugs. A developer reviewing the output might spend hours debugging what appears to be a logic error, never realizing the root cause was two agents with overlapping mandates and no arbitration rule. This is exactly the same failure mode as two developers on a team who were never told who owns a module. The AI didn't cause the problem. The missing engineering discipline did. There's an even more dangerous failure mode than duplication, and it's harder to detect. Now for the failure mode that's harder to catch and more expensive to fix, hallucination propagation. Here's how it works. Agent A is generating a data model. It hallucinates a field. Let's say it invents a user attribute that doesn't exist in the actual requirements. Agent B receives that output and builds business logic around user tier. Agent C writes API endpoints that expose user tier. Agent D generates front-end components that display user tier. By the time a human reviews the output, 4 layers of coherent, well-written code have been built on top of a fiction. And because each individual agent's output looks locally correct, no single piece triggers an obvious red flag. This is a cascade failure, identical in structure to what happens in a system without integration tests, where a wrong assumption in a data layer silently propagates through service layers and surfaces only in production. The fix in classical SW engineering is a verification gate, an integration test that checks the contract between layers before the next layer builds on it. In multi-agent systems, this maps to a test agent, a dedicated verification stage that validates each agent's output against the original requirements before downstream agents receive it. Without this gate, your pipeline is one hallucination away from a full rebuild. Coming up next, we'll look at which tools actually give you control over these verification gates, and which ones abstract it away in ways that will cost you later. Now let's get practical and compare the 3 dominant options engineers are actually using: Cursor in agentic mode, Claude Code, and custom multi-agent setups. These tools sit at very different points on the control versus convenience spectrum, and picking the wrong one for your context is a genuine engineering mistake. Cursor gives you tight IDE integration and a smooth developer experience, but its agentic mode is largely a black box. Task decomposition happens internally. You have limited control over how the problem gets split, and integration flexibility is constrained to what Cursor's workflow supports. It's excellent for individual developers on bounded tasks. Claude Code sits in the middle. It exposes more of the agentic reasoning, supports tool use and multi-step workflows, integrates with external systems via API, but engineering overhead is moderate, and you're still working within Anthropic's execution model. Custom multi-agent setups, built on frameworks like LangGraph, AutoGen, or raw API calls, give you full decomposition control, explicit interface contracts, custom verification gates, everything we've been talking about. But the engineering overhead is high. You are building the orchestration layer yourself. The right answer isn't the most powerful tool. It's the right tool for your team's current engineering maturity. And that's exactly what the next scene will help you determine. So how do you actually decide which tool to use? Here's a decision framework built on 2 axes: your team's SW engineering maturity and the structural complexity of the problem you're solving. First, ask whether your team can define explicit task boundaries before writing any code. If the answer is no, Cursor is your ceiling, and that's not an insult, it's the right call. Second, ask whether your system has more than 2 integration points between components. If yes, you need visibility into the agent interface layer, which means Claude Code at minimum. Third, ask whether failures in production are recoverable at low cost. If not, if you're building for healthcare, finance, or regulated systems, you need explicit verification gates, which means custom agents with defined test stages. Fourth, check team size and coordination overhead. Custom agent frameworks require someone to own the orchestration architecture. If no one on the team has done that before, the framework will become a liability faster than it becomes an asset. Fifth, consider iteration speed requirements. If you need to fast and learn fast, Cursor's low overhead wins in the short term. The framework isn't about finding the best tool in the abstract. It's about finding the tool that matches where your team actually is. In the next chapter, we're going to take everything from this chapter and walk through a multi-agent design, applying divide and conquer from first principles to a concrete problem. That's where these abstract patterns finally become something you can use on Monday morning. Not every problem deserves a multi-agent solution. In fact, throwing multiple agents at a simple task is one of the fastest ways to create a system you can't debug or maintain. So before we design anything, we need a filter, a set of criteria that tells us whether a problem is actually a good candidate for decomposition. 3 signals matter most. First, complexity threshold. The problem must be large enough that a single agent context window or a single prompt chain collapse under the weight of all the requirements. Second, domain separability. The problem must contain natural fault lines, subdomains that don't deeply entangle with each other at execution time. Third, and most critically, verifiability. Each subtask must produce output you can independently check. If you can't verify a subtask in isolation, you can't trust the integrated result. Miss any one of these 3, and your multi-agent system will be harder to manage than a monolith. But here's the thing. These criteria map directly to classical decomposition heuristics from software engineering. You've seen this logic before, just in a different context. Let's put these criteria to work on a real problem right now. Let's make this concrete. The problem we're going to walk through is building a dynamic promotion engine for a mid-scale e-commerce platform. Here's what it needs to do. It has to analyze a user's purchase history, apply eligibility rules for multiple concurrent promotional campaigns, calculate final discounted pricing including tier-based loyalty adjustments, generate a personalized promotional message, and log the entire decision trail for compliance auditing. Now run this through the 3 filters. Complexity? Absolutely. 5 distinct concern areas, each with its own data model and business logic. Domain separability? Yes. Eligibility checking. Pricing calculation, message generation, and audit logging share almost no runtime dependencies. Verifiability? Each output, eligibility result, calculated price, message copy, audit record, is independently testable. This problem passes all 3 gates. It is a strong multi-agent candidate. And notice something, we didn't need AI to tell us that. We used classical requirements analysis. That's the point. Now let's decomposing it, and the first design decision is going to surprise you. Here's the first design decision that trips people up. How granular should each agent be? The temptation is to create one big promotion agent that does everything. We've seen this pattern before. It's called a God object in OP, and it's just as dangerous in agent design. The single responsibility principle applies here just as cleanly as it does to classes. Each agent should own exactly one well-defined concern. So we decompose into 5 agents. A user profile agent that fetches and normalizes history, an eligibility agent that evaluates campaign rules, a pricing agent that calculates final price, a message agent that generates copy, and an audit agent that records the decision trail. Notice the mapping. Each agent corresponds directly to one of the 5 concern areas we identified in requirements. This is not a coincidence. It's the payoff of doing requirements analysis before jumping into implementation. Each agent has a clear input, a clear output, and a boundary it does not cross. But defining roles is only half the work. The harder half is defining what agents say to each other. And that's where most multi-agent systems fall apart at integration time. Now here's where software engineering discipline separates good multi-agent systems from fragile ones. Once you've defined your agents, you must define their contracts, explicit input and output schemas that every agent agrees to honor. Think of it as an API contract between microservices, but for agents. Without this, you get what I call the whisper chain failure. Agent A produces output in a format Agent B didn't expect, Agent B silently misinterprets it, and the error surfaces only at the very end as a wrong final answer with no clear blame. The schema forces the error to the boundary, not the middle. Here's what a contract looks like in practice for our eligibility agent. The input schema specifies a user id as string, campaign list as an array of campaign IDs, and a user profile object with tier and purchase count fields. The output schema specifies an eligible campaigns array and a reason map, a dictionary explaining why each campaign was accepted or rejected. Every field is typed, every field is documented. This is not over-engineering. This is the minimum viable contract that makes integration testable. And the next piece, the orchestrator, depends entirely on these contracts being honored. With agents defined and contracts written, we need the orchestrator, the component that knows the execution order, manages dependencies, and handles failure recovery. Think of the orchestrator as the project manager of your agent system. It doesn't do the work itself. It knows who does what, in what order, and what to do when something breaks. For our promotion engine, the dependency graph looks like this. User profile agent runs first, because every other agent needs its output. Eligibility agent and aud agent can both start the moment user profile agent finishes. They're independent of each other, so we run them in parallel. Pricing agent depends on eligibility agent output, so it waits. Message agent depends on both eligibility agent and pricing agent, so it runs last before aggregation. This is a classic DAG, a directed acyclic graph, the same structure used in CI/CD pipelines, build systems, and workflow engines. The orchestrator encodes this graph explicitly. It does not let agents self-organize or assume execution order. Explicit is always better than implicit, especially when you're debugging a production failure at 2 am. But scheduling is only half of the orchestrator's job. What happens when an agent returns an unexpected output, or times out entirely? That's where error recovery design comes in, and it's the part most teams skip. Here's a hard truth. In multi-agent systems, agents lie. Not intentionally, but an LLM-backed agent can return output that looks correct syntactically and is completely wrong semantically. A pricing agent might return a valid JSON object with a negative discount value. An eligibility agent might return an empty array when it should have matched 3 campaigns. Without a verification layer, these errors flow silently into your final output. The solution is a verifier agent, a dedicated component that sits between each worker agent and the aggregator, and checks every output against the defined contract before allowing it downstream. In code, this looks like a validation function that receives the agent's output and the expected schema, checks required fields, validates value ranges, and flags anomalies. For our pricing agent, the verifier checks that final price is a positive number, that discount applied is between 0 and 1, and that the applied campaigns list is a subset of the eligible campaigns from the previous step. If any check fails, the verifier triggers a retry or escalates to the orchestrator. This is the automated equivalent of integration testing in classical software engineering, except it runs at runtime on every execution. The question is, what happens when multiple agents all pass verification individually, but their outputs conflict with each other when combined? That's exactly what the synthesis step handles. The final phase is synthesis, and it's the most underestimated step in multi-agent design. You've collected 5 verified outputs. Now you need to merge them into a single coherent result and validate that the integrated output still satisfies the original requirements. This is not trivial. Consider a conflict. The eligibility agent returns 2 eligible campaigns, but the pricing agent only applied 1. Is that a bug or a business rule? The message agent generated copy referencing a discount that the pricing agent actually zeroed out due to stacking rules. These are cross-agent consistency failures that no individual verifier would catch. The synthesis step must define explicit conflict resolution rules, priority ordering, override logic, and a final validation pass against the original requirements specification. In our promotion engine, the synthesis step merges all outputs into a promotion result object, runs 3 cross-agent consistency checks, and writes the final state to the aud agent log. If any cross-check fails, the entire pipeline rolls back, not just at the failing agent. This is the same transactional thinking you'd apply to a distributed database write. The lesson of this entire walkthrough is simple. Multi-agent design is not a new discipline. It is classical software engineering, decomposition, contracts, dependency management, integration testing, applied to a new execution model. Which brings us to the most important question of this lecture series. What does this mean for you as a developer in the agent era? What skills actually matter now, and which ones are becoming obsolete? That's exactly what the next chapter answers. Here is the uncomfortable truth that nobody in a coding bootcamp is telling you right now. When AI can generate a working function in 3 seconds, the ability to write that function is no longer your competitive edge. Full stop. What becomes scarce, and therefore valuable, is everything that happens before and after the code gets written. Think about it this way. AI is an extremely fast, extremely literal executor. It does exactly what you describe. So if you describe the wrong thing, it executes the wrong thing perfectly. The skills that multiply in value are the ones that define what the right thing even is. Problem structuring. Can you decompose a vague business requirement into a precise, testable specification? System thinking. Can you see how a change in one module ripples across 5 others? Architecture skill. Can you design boundaries that make the system extensible without becoming fragile? And verification ownership. Can you build the tests and contracts that catch the AI when it drifts? These 4 layers form the new competency stack. The developers who master them will direct armies of agents. The ones who don't will spend their days correcting agent mistakes they never learn to anticipate. And here, the question you should be sitting with right now: how much of your current skill investment is in the bottom layer versus the top? Let's be precise about something that often gets confused in the industry right now. Prompt engineering and architecture design are not the same skill at different depths. They are fundamentally different disciplines, and conflating them is costing developers their careers. Prompt engineering is a surface skill. It is valuable, do not dismiss it, but it operates at the level of a single interaction. You craft an instruction, the model responds, you refine. The feedback loop is fast, and the scope is local. Architecture design, on the other hand, operates at the level of a system over time. You are defining how components relate, how state flows, how failures are contained, and how the system evolves when requirements change. Now here is where it gets interesting for our context. In a multi-agent system, the system prompt is actually a specification document. It defines the agent's contract with the rest of the system, its inputs, its boundaries, its error behavior. Writing a good system prompt for a production agent is not a prompt engineering task. It is a software specification task. That reframe changes everything about how you approach agent design. You are not chatting with an AI. You are authoring a component interface. The developer who understands this is not a prompt engineer, they are an agent system designer. And that role, nobody is automating it. Next, we will talk about exactly how to position yourself in that role and what your career trajectory looks like from here. If you are a senior developer or tech lead watching this, I want you to hear something clearly. You are not being replaced. You are being given leverage you have never had before. Think about what a senior engineer's real value has always been. It was never raw typing speed. It was the ability to see the whole system, anticipate failure modes 3 steps ahead, decompose a complex problem into a set of solvable pieces, and review whether a solution actually fits the architecture, or just looks like it does. Every single one of those skills is now a force multiplier in an agent-driven environment. You can now direct 10 agents doing parallel implementation work. You can define the contracts they must satisfy. You can write the integration tests that validate their outputs. You can catch the architectural drift before it becomes technical debt. The developers who get displaced in this era are the ones whose entire value was in fast implementation. The ones who could write a Redux reducer quickly, but never understood why the state was structured that way. The architects, the tech leads, the engineers who always cared about the why, they become the orchestrators of entire development pipelines. Your SW engineering experience is not a liability. It is the exact skill set that makes agent systems trustworthy. But there is a catch, and we will get right now. So what should you actually study or restudy right now? Not frameworks. Not the latest LLM API. Those change every 6 months. I want to give you the durable list, the skills that will compound in value regardless of which AI tool dominates next year. First, requirements engineering and specification writing. The ability to write a precise, unambiguous requirement is the foundation of a good agent instruction. If you cannot write it for a human developer, you cannot write it for an agent. Second, design patterns, specifically the ones that govern boundaries, ports and adapters, command query separation, event-driven interfaces. These are the patterns that let you isolate agent behavior and test it independently. Third, contract-first API design. Before any agent writes code, the inner contract must exist. Open API specs, JSON schema, type contracts, master this. Fourth, observability. In a multi-agent pipeline, when something breaks, you need to know which agent broke it and why. Structured logging, distributed tracing, and correlation IDs are non-negotiable. Fifth, testing strategy, not just tests, but contract tests. End-to-end or serial tests that deliberately try to break your agent's assumptions. This is the stack that makes you dangerous in the agent era. And here is the honest question. How many of these did your last project actually use? The final dimension of this shift is organizational. Teams are being restructured around AI-augmented workflows, and the roles inside those teams are changing in ways that most job descriptions have not caught up with yet. Here is what the new model looks like in practice. At the top, you have the system architect, the person who defines the overall agent topology, assigns responsibilities to each agent, and owns the integration contracts. Below that, you have agent operators, developers who configure, monitor, and tune individual agents within the system. They own the system prompts, the tool definitions, and the output validation logic for their agents. Then you have quality engineers who own the contract testing layer, ensuring that every agent's output conforms to the system contract, and that the system as a whole behaves correctly under failure conditions. And underneath all of this, you have the AI agents themselves as execution contributors, not replacements for people, but nodes in a managed pipeline. The SU engineer does not disappear in this model. They move up the stack. They become the person who designs the pipeline, defines the contracts, and ensures the whole system is trustworthy, not just functional. This is the role that is open right now. The organizations building serious agent systems are desperately looking for engineers who understand both software architecture and how to manage AI behavior. And in our final chapter, we will talk about what kind of developer wins in this environment, and what they never stop doing even when everyone else chased the AI hype. Let's bring everything together. Across this lecture, we made 5 core arguments, and every single one points to the same uncomfortable truth. First, AI coding tools don't eliminate the need for SW engineering. They amplify the cost of skipping it. A bad architecture copied 1,000 times by an agent is 1,000 times worse than one bad function written by hand. Second, multi-agent systems are not a new paradigm for software. They are distributed systems, and distributed systems have been punishing sloppy design since the 1970s. Third, the failure modes you see in AI-generated code, tight coupling, missing contracts, non-deterministic state, are not AI problems. They are engineering problems that AI makes visible faster. Fourth, prompt equality is a downstream effect of thinking clarity. Engineers who understand separation of concerns write better prompts because they think in cleaner boundaries. Fifth, and most important, the execution actor changed. The machine now writes the code. But the essence, requirements, design, contracts, verification, modularity, that has not changed, and it never will. The developers who understood this from the start are already pulling ahead. The ones still chasing the fastest prompt are going to hit a wall. And we'll show you exactly what that wall looks like in the final scene. Here is the final message, and I want you to remember this one sentence above everything else we covered today. The developers winning the AI era are not the fastest prompters. They are the clearest thinkers about structure. Speed is easy to copy. A competitor can learn your prompt template in an afternoon. But the ability to decompose a complex system into clean, verifiable, independently deployable components, that takes years to build, and it cannot be automated away. Because the AI needs someone to tell it where the boundaries are. It needs someone to define what done means. It needs someone to catch the failure that looks like success. That someone is the engineer who never stopped engineering. The question is not whether AI will replace developers. The question is which kind of developer AI makes irreplaceable. And now you know the answer. Go build something well-structured. And your next step is right after this. Before you close this tab, I want to give you 3 concrete actions, not vague advice, 3 things you can actually do. Action 1, do this today. Take the last AI-generated module you shipped or reviewed and draw its dependency graph by hand. Not with a tool, by hand. If you can't draw it cleanly in 5 minutes, that module has an engineering problem, and now you know where to focus. Action 2, study this next, go deep on one of these 3 topics: formal interface contracts and API design, observable design for distributed agents, or property-based testing for non-deterministic outputs. Any one of these will compound your value as an engineer for the next 5 years. Action 3, bring this question to your next architecture discussion. If every component in this system were replaced by an AI agent tomorrow, boundaries would hold and which ones would collapse? That question will expose more design debt than any code review. If this lecture shifted how you think about AI and engineering, subscribe. Because the next video goes deeper into multi-agent orchestration patterns, and the traps are even less obvious than the ones we covered today.